So today's lecture is somehow connected to the one on Monday. We are going to look at normal lines. Two vector sets, well, two level sets in R3. But level sets in R3 are actually surfaces. And we are interested in describing the lines perpendicular to a surface, a level surface, at a certain point. So let's begin with a function. So we have a function. On a domain D in R3, but we don't need to specify the domain. Well, by now we should know that it's impossible to draw the length of the function. So we have to look at its level sets instead. So we fix a number k. A real number k. May be positive, it may be negative, it may be 0. Then we are going to define the following level set. So we define this LK. The level set at level K to be the set of all the points which we denote by X, Y, and Z. is the set of all points in D for which the value of f is equal to k. Okay. So we look at all those points which make the value of f to be equal to k. Okay. This is the description of a level set. And in terms of geometry, this LK here, the level set LK here is a surface. Call that S. Okay.
Sir, I have a question.
Mhm.
So would K indicate the level number
Yeah.
for this?
Yeah.
Okay. And LK is just like the actual level in the surface.
That's correct. Yeah.
Yeah. So LK is a surface and it's a level. Okay.
Well, we look at some pictures before. Now let's look at one particular. Well, for example, we can have a whole bunch of concentric spheres, right? At the origin. You have a whole bunch of concentric surfaces at the origin. And each surface is a level set. But the levels of all these level surfaces cannot be negative. Right? It cannot be negative because the radius cannot be negative. But it can be any number from 0 to infinity. Okay. So let's look at one of them. Well, of course, in general, you don't have a sphere, but rather a surface like this. So this is the surface S. Now I am going to look at a point. Call it P. And it has coordinates x naught, y naught, and z naught. Okay, a point P. So we have an arbitrary point. In the surface. Okay. Now, what is a normal line? To the surface. At the point x naught, y naught, z naught. Well, I think you can visualize or imagine what it should be. But how do you describe it precisely using mathematical language? So, do you want to try?
It's like a cross section.
Why is it a cross section? What's a normal? Normal means what? Perpendicular.
Perpendicular.
Perpendicular to the surface, but the surface is, well, for a sphere, you can visualize the surface.
Normal line to the tangent plane.
A normal line is normal to
Yeah, normal to the tangent plane at the point.
the tangent plane.
Yeah.
Exactly. There are many tangents. Okay. So it's going to be a line perpendicular to the tangent plane to the surface S at the point P. That's why I said that today's work is somehow related to the work on Monday. So a normal line to S at the point P is a line perpendicular to the tangent plane. to the tangent plane to the surface. At E. Okay. That's the mathematically precise language for a rhomboid line. Okay. Okay. We have a mathematical language. And then we want to work with it. Or we want to describe it. And we need to find this equation. That's the interplay between geometry, pictures, and equations. Okay. So we are going to find equations. There are many forms of equations, but the one that we need or we prefer is the one that we use in linear algebra. We are more interested in parametric equations. So we are going to find parametric equations. Of this normal line. Okay. So that's the whole program for today. Well, again, you can visualize what that tangent plane looks like. Well, it's a plane in R3, tangent to the surface at this point. Okay, so if you want to look at a portion of it, it could be something like that. Right? Of course, this is only a small portion of the whole tangent plane at this particular point. So let me take this out and magnify it. Okay. So this is the tangent plane to the surface S at the point P. So is it simple or easy? Or can you figure out what a perpendicular vector to this plane at the point P? Can you give me one? What did we do on Monday?
Could find the normal vector by taking any two vectors on that plane and taking a cross product.
No, we don't do it this way. What did we do it on Monday? It's somehow related to the function. Anybody?
Well, we
Did we
determined.
take the dot product?
Do we find the gradient at the point?
Area, exactly. Okay, that's exactly what I want you to tell me. So we can find a vector. Well, you can use cross product, but why don't we do it more directly? When there is a more direct method. So a vector perpendicular to the surface at the point P is the gradient of the function f at the point P. Certainly more direct, more efficient to use the gradient than calculating the cross product of two vectors. All right. Well, the formula for this is the partial of f with respect to x. At x naught, y naught, z naught. and then the partial of f with respect to y at x naught, y naught, z naught. And finally, we have the partial with respect to z at x naught, y naught, z naught. Let me make this bracket bigger. Okay. So we have a vector matrix. And it's perpendicular to any vector in this tangent plane at this point. But this one is not important for us now. Okay. So you see, this gradient is perpendicular to the tangent vector to every curve lying in S at the point P. Okay. And to calculate the tangent plane, you only need two tangent vectors. And then we calculate the cross product. That's how we did it at the beginning. Okay, but at that point, I told you that the tangent plane should contain every tangent vector, not just two. All right. This is the gradient of f. At the point x naught, y naught, z naught. Okay. All right. Once you have a perpendicular vector to the tangent plane, then you can have the line perpendicular to the tangent plane. And that perpendicular line passes through the point P. So we have something like this. Actually, you cannot see this part. So you should use dotted lines. This is the part that you cannot see. Okay. So this is the normal line. Let's call that L. L is not good. We already use it for the level set. Let me use small a.
Sir,
Mhm.
I just have a quick question. So the parallelogram represents the tangent plane and the line going through it is the normal line?
Yeah.
Okay.
Okay. Exactly. But in a two-dimensional board, that's the best one can do. Okay. How are we going to find an equation for the normal line? Well, your high school mathematics or first year mathematics told you to do the following thing. Take a point. Arbitrary point. So you take an arbitrary point x, y, z in L. So we let x, y, and z be in the normal line. And then you want to find an equation satisfied by this arbitrary point, x, y, and z. Find an equation for x, y, and z. Okay. Now, the way to do it is quite similar to what we did on Monday. So I am going to look at the vector with terminal point x, y, z, and initial point x naught, y naught, z naught. Okay. All right. So let me say I can find another vector. Perpendicular to the tangent line. Or maybe it's better to, okay, perpendicular to the tangent plane. to the surface S. At the point P, with initial point x naught, y naught, z naught, and terminal point x, y, and z is what? So let me write a vector in this form. Without I, J, and K. What's the first entry?
Would it be x minus x naught
That's correct.
over the partial derivative of fx?
Then that's,
Or no?
then that's not correct.
Okay.
Your
X
is
minus
not
X.
correct. It's just x minus x naught.
Okay.
X minus X naught, Y minus Y naught, and Z minus Z naught.
Correct. Okay. So we have another vector. Perpendicular to the tangent plane. Okay. Now, what do you know about this longer vector and this shorter vector? I think I have used the word or one word to describe this situation.
Is it
Linear.
collinear?
Collinear, right? Or sometimes they are parallel, okay? But this is more than being parallel. So these two vectors, the longer vector and the shorter vector, given by the gradient, are collinear. They lie on the same line. So x minus x naught, y minus y naught, and z minus z naught. And the gradient of f at the point x naught, y naught, z naught. Are collinear. Okay. If they are collinear, how do you describe this phenomenon mathematically?
Two vectors are scalar multiple.
They are a scalar multiple of each other. And how do you write it mathematically?
Using a parameter t, like
That's right. So That's where the parametric equations come from. And that's the form of the equations that I usually prefer. I will tell you why. So the vector x minus x naught. Well, actually, you did something like this in the first test. Except that it's simpler. So this is a scalar multiple of the gradient. And the gradient is given by this. I don't need this now. Okay, where t is any real number, can be negative. So t is any real number. Okay. So now I am going to equate the components in these two vectors. So what do we get?
So we'll get a x minus x naught over the partial derivative of f with respect to x. Well, x minus x naught divided by the partial derivative with respect to x at x naught, y naught, z naught equals t. And then
Yeah,
you do the same thing for y minus y naught, z minus z naught.
exactly the form that I don't prefer. All right. I will tell you. But let me put down the form I prefer first. So this tells us that we are able to get x minus x naught is equal to t times the partial derivative, right? Which is df dx at x naught, y naught, z naught. But I can put it in a better form. So x is equal to x naught plus t times the partial derivative. and you have Y, and you have Z. Similar.
So sir, so would this give us a vector that is part of the normal line? The X, Y, and Z? That's a vector part of the normal line?
This is not a line. This is a point in the
Yeah, a point in the normal line.
okay.
Okay,
It's point in the normal line. And they satisfy these systems of equations.
okay.
Okay. And finally, Z is equal to Z naught plus T times the partial with respect to Z. At X naught, Y naught, and Z naught. For T, let me put down all the commas. In the set of all real numbers. So every point X, Y, Z in the normal line satisfies this system of equations. And we call these the parametric equations. Okay. Now, give me 1 minute. To put down the form that I said that I don't prefer. Put them on. A student already pointed out that we can have an equation like this. X minus X naught over the derivative is equal to T. And actually all of these fractions are equal to T.
So pretty much these are the symmetric equations.
You can call that symmetric equations. There's certainly symmetry in it. This is the set. and they are all equal to t. But you cannot always have this. What's the drawback?
Well, if the partial derivative with respect to x at x naught, y naught, z naught is equal to 0, then it wouldn't work out, right?
Then it doesn't work.
Yeah,
If any one of them is equal to 0,
yeah.
it doesn't work out. Okay?
So it's better to use the other equation that you said, and that's why you said it's better, right?
Yeah.
Okay.
Whenever you have division, you have that trouble. Right? So this is a good point to start. But this is, some people also use this when they are not equal to 0. When none of them is 0. It's good. But you have to check them. Okay?
But sir, even if it is equal to 0, can't you just use that to multiply it by t, and then it just becomes x minus x naught equals to 0?
Yeah.
Oh yeah, but then it's going to say x naught is equal to x,
Then
for
x,
example.
then x is equal to x naught.
Yeah.
So that's no problem.
So that would basically say that there's no other point in the normal line that is perpendicular to the tangent plane, just the x naught, y naught, z naught.
Let's examine that case. So if this one is equal to 0, and x is equal to x naught. Okay? What's the graph of x equal to x naught?
A constant plane
Which plane?
on the x-axis.
Parallel to XY, YZ plane.
Let me write it like this. So you have a plane at x naught. Okay? X is always equal to x naught. And what's the plane? If x naught is equal to 0, you get the YZ plane. So you have the YZ plane moved to this position. Okay, that's a plane. Okay. The plane is moved to this position if x is equal to x naught. Okay,
I have a question. In that case, what is happening? What are happening? Y and Z?
what happened to the y-axis?
Y and Z. In that case, if a partial f over partial x is 0, then our x is equal to x is 0, right?
Yeah.
Then this means t is 0 in the symmetric equation.
Well, when x is equal to x0,
Oh yeah, t can be any number.
t can be any number.
Then how we define the fraction ratio?
There's no t. Okay. So it's undefined. So you have x minus x0 over 0
Yes.
equal to t. It doesn't work. Okay. But if you use the parametric equation, the line is x equal to x naught, y is, what is it? Y naught plus t times the partial of f with respect to y and then z
Z naught plus T, the partial derivative.
Yeah.
Of F respect to Z.
z is z naught plus df dz. I hope you can see it. At x naught, y naught, z naught. Okay. And these are the parametric equations. Okay.
Sir,
Yeah.
can I just ask one more question about this?
Go on. Yeah, go ahead.
So if x minus if x minus x naught is equal to 0, so right now I'm looking at the equation that you don't prefer. So if x minus x naught is equal to 0, then wouldn't everything also equal to 0? So y minus y naught over the partial derivative of f with respect to y also equal to 0 as well. So y equals y naught.
I forgot the T. These are the parametric equations. Okay, it works for all T.
Okay.
It works
Yes, sir.
for all T. But if you use the symmetric form, the first term doesn't make sense.
Yeah.
That's the point.
Okay. So yeah. So that's why you prefer this one. Yeah. So it's less
This
confusing.
one always works.
Yeah. Yeah.
Okay.
Okay. So yeah. So symmetric parametric equations gives you problems when the partial derivatives are equal to 0.
No, the symmetric forms give you a problem.
Yeah.
When
Yeah.
the partials one of the partials
Yeah,
equal to 0.
okay.
And for this one, what happens?
Well, just be keep on changing because t is
Well, if,
any number.
if all of them are equal to 0, if all the partial derivatives at that point are equal to 0.
Then it's just
then
x equals x naught, y equals y naught, z equals z naught.
You get a point.
Yeah,
Okay.
okay, that makes sense.
All right.
So you got to be very careful which form you use.
No, I usually specify which form you have to use.
Okay.
Okay.
All right, thanks, Professor.
Yep.
Have a good day.
You too. Okay, so maybe we should stop here today. All right.